All right, so we have, in addition to enthalpy as one of the principles that decides whether or not chemical reactions happen, we like to have enthalpy go down, right? We like things to be exothermic because energy gets more spread out. There's also something called entropy. And the idea of entropy is considered to be the degree of matter and energy dispersal. The idea is matter likes to be more spread out. It's the way of the world. It's naturally matter gets more spread out. And so the example here, you can see in with the hydrogen and oxygen with these gas vessels connected by a stopcock. If the stopcock here is closed in the leftmost graphic, and I open the stopcock eventually, the oxygen and the hydrogen particles will become more spread out. This will happen naturally, okay? And that's the idea of entropy, and that matter will on its own become more spread out, okay? Entropy is a measure of the degree of matter and energy dispersal in a substance, okay, or in a system. Again, sometimes it's called the disorder or randomness of the system. College Board and many chemists don't like you to say disorder and randomness. I would stick with degree of matter and energy spread. That's a good way to think of it. The symbol for I am entropy. I am entropy. Mr. S. S is entropy. And entropy is S. I am disorder. No, I'm kidding. But the symbol is capital S. I'm not sure why. Why it's S. And a change of entropy then would be a delta S. Interestingly enough, the units of entropy have an energy term and a temperature term. Just the way it is, it's joules per Kelvin degree, okay? Or if you're talking about the entropy contained in a mole of a substance, joules per mole degree Kelvin. You know how delta H is kilojoules per mole, the mole, like that, like we looked up on the goldenrod colored paper, right? Your delta H formations, kilojoules per mole. You'll look on there, and if you eventually going to want to get the orange sheet out, that goldenrod colored sheet, you'll see that the units of entropy, and that's that next column over from the delta H formation, is the entropy column, and it's in joules per mole degree C, because those are the molar entropies for those substances, okay? So if we look at a substance, all right, and that should be S superscript 0, that here, this should be like, I don't know what happened, that should be S0, like up in the air, okay? Like standard absolute entropy, right? Anyway, qualitatively, not quantitatively, because we're going to do some quantitative stuff with entropy in a little bit, but qualitatively, let's look at some conditions where something might have more or less entropy. Okay, if matter likes to be more spread out, what are some conditions where matter would be more spread out versus less spread out? Like, could I think about, I have a bag of lead here, these lead atoms in this baggie. If I wanted to know like what their degree of matter spread is, sitting right here in this baggie, right? And would they have a relatively low entropy or a relatively high entropy? Okay. So one of the things we can think about qualitatively is the state of matter. Well, just thinking about how they are at the subatomic level, gases have more entropy than liquids. The particles in a gas are more spread out, all right? Right? And the entropy of a liquid would be in between. Solids have the least entropy. So if you kind of wanted to summarize kind of this, you could say something like the entropy of a gas was greater than the entropy of a liquid, which is greater than the entropy of the solid of that same substance anyway. And we're going to put the standard entropy. And that would be the entropy measured at, like it said on the goldenrod paper, the table of thermodynamic constants. That's going to be your standard entropy. So the entropy at 25 degrees C and normal air pressure. Okay. But either way, right? Gas particles are naturally more spread out than solid particles. How about temperature? Well, think of the Maxwell-Boltzmann distribution, and guess who had his hand in determining the mathematics behind statistical considerations of entropy? Good old Maxwell-Boltzmann himself, right? So if you think again, we're going to think about a graphic that we've looked at a lot, right? This would be your kinetic energy here, right? Going increase in this is the number of particles with that kinetic energy. Remember, at a lower temperature, there's a distribution like this. If I raise the temperature, remember what happens to the average kinetic energy of every particle increases. And you can see then that things at a higher temperature will have greater entropy. Yes. Greater entropy contained in that sample. So this lead, which is at room temperature, if I warmed it up, it stayed a solid. But if I warmed it up to like 100 degrees, it wouldn't be melting yet. It doesn't melt until like over 200 degrees, but it would have more entropy because the particles would be at higher temperature. And then finally, molecular complexity. The more atoms, that's a little star, okay, in a compound, the more individual particles that are vibrating, okay? So I always give the example, for me the example is of carbon monoxide versus carbon dioxide. In a mole of carbon monoxide, well, there's only 2 atoms, and we know what happens to these atoms. They're vibrating around each other. They're bonded together, but they vibrate and they rotate, right? All that rotational motion, all that vibrational motion along that bond, that's all contributing to the entropy of that substance. Yes? Well, in CO2, CO2 has 2 bonds with carbon. Right, and there's more atoms in there bouncing around the central carbon in CO2. Okay, so the more bonds you have, the more atoms you have, the more individual particles that are vibrating, then the higher the natural entropy you would have. I know there's a lot here. I probably could have given you the printout of these, but anyway, let's look at changes in entropy for different processes, either chemical or physical processes. So let's think about this. So there's going to be 3 main things you could be asked to estimate whether or not you thought entropy would increase for this reaction. So how about water liquid becoming a gas? Well, you already know. Or wax liquid becoming wax solid. So you're going to look at this and since this is a change of state, you're going to look at the states of matter. Well, we just said, gases have a higher entropy than liquid water, right? And so you would expect then that the entropy would increase, wouldn't it? If something went from a liquid to a gas. How about wax going from liquid to solid? Well, we already know solids have lower entropy and liquids have a higher entropy. So the entropy is going to decrease, which means that the degree of microstates or the randomness or the matter is going to become less spread out, right? This means matter is going to become less spread out, right? And so all you're going to be asked to maybe say is, do you think that the delta S would be a positive number? That is, would the entropy increase, which is favorable, natural, or would the entropy decrease, okay? How about the dissolving process? Well, let's think about the dissolving process. First of all, you start out with something as a solid, for example, NaCl. And when it dissolves, first of all, if it's ionic, the particles break apart. So here you have 1 mole of a particle, right? And here it makes 2 moles of particles. And not only that, those particles are aqueous. They're floating around in a liquid attached to water, right? This is going to be a very large increase in entropy, yes? Even if it's not ionic, even if it's covalent and it's a sugar, then glucose dissolves because of the intermolecular forces, right? That glucose molecule is a solid here, rigidly held. When that glucose dissolves, that glucose molecule is going to be floating around attached to water. Much more freedom, much more spread out matter. So dissolution or dissolving, with very few exceptions, and we'll talk about this we have like a little 20-minute notes at one point on just on dissolving energy and entropy changes. Okay, it'll be after we do all of the entropy stuff. But anyway, with few exceptions, when something dissolves, it becomes more spread out. Okay. Sometimes, well, I'll kind of give you a little teaser. Why would something have less entropy if it dissolves? Well, what if when it dissolves, the intermolecular forces are so strong, they cause it to be more rigidly held, right? That would actually maybe decrease the matter spread. It doesn't happen very often. It happens in a few select cases. So that's the bottom line on that. Well, how about chemical reactions? If you're asked to estimate whether a chemical reaction would result in an entropy increase or decrease, here's the main thing you're looking at. You're looking at the numbers of moles of particles and maybe even their size, but mainly you're looking at the number of moles of particles. For example, when 2 hydrogens and 1 oxygen combine to make water, here you have 3 moles of a gas, and they're making 2 moles of a gas. Imagine those gas particles in a box. 3 moles bouncing around has more matter spread than 2 moles bouncing around, don't they? Yes? So this would cause a decrease in entropy. They're all gases, right? How about the decomposition of calcium carbonate so it's a solid, it's a single particle breaking up into 2 moles of particles, and one of those particles is a gas. That's going to be an entropy increase, isn't it? You're decomposing, and not only that, now if you decomposed into 2 solids, it would still be an increase in entropy, but not as great, okay? But one of those is a gas. How about this combustion reaction? The combustion of propane. Well, there are 6 moles of gas on the left-hand side, 7 moles of gas on the right-hand side. You would predict that the entropy is going to increase, and you don't even need to know what the absolute entropy of water is, what the absolute entropy of hydrogen is. This is all qualitative, not quantitative. Okay? So again, you might be asked to determine whether you thought this process would result in an increase or decrease in entropy. And this is how you do it. So now, gentlemen, we're going to get quantitative, okay? Again, what if you wanted to know what the entropy change for a reaction or a process was? And you're given a table of those standard entropies. This is this is on that goldenrod sheet, right? That goldenrod paper. The tables of thermodynamic data. Again, that second column over, it says that it's the S0, right? That's the absolute standard entropy, and this is the entropy contained in that substance. How they measure it, we're going to finally get to. At some point when we finish this all, we'll get an idea of how could they possibly measure that. Okay? How could they possibly measure the entropy contained in a molecule? There are ways. Okay? But anyway, so you can use the absolute entropy table to calculate the change in entropy for a reaction or for boiling or melting, as long as you have those entropies, right? And it's going to be the same equation as we used for delta H RXN. Remember, to delta H RXN, it was the sum of the delta H formation of the products, right? Minus the sum, sorry, I'll only use the sigma sign, sorry. The sum of the delta H formation of the reactants. Okay, well, it's the same here. It's the exact same with entropy. You can calculate the change in entropy, not qualitatively, but quantitatively. So let's go through this example. What would be the delta S would be the change in entropy for a chemical reaction, okay, if for this reaction. 2 carbon monoxide plus oxygen makes CO2. So what I'm going to do is I'm going to go to my molar entropy table. I'm going to look up carbon monoxide. Its entropy is 197.6 joules, not kilojoules. It's important. Joules per mole Kelvin. But there's going to be 2 moles, isn't there? So when I have to multiply that number times 2, because that's how much entropy is in 1 mole, but there's 2 moles. For oxygen, now entropy for an element in its natural state is not 0, only enthalpy, right? So because this isn't a change, this is the absolute entropy contained in oxygen. It's in the column number, the second column, 205. This is 205.0 joules per mole Kelvin, and there's 1 mole. How about the CO2? Well, CO2 has more absolute entropy. It is 213.8 joules per mole Kelvin, and there are 2 moles of it in this reaction. Okay, come on, Mr. S, you have the numbers written right down here. So but this is how I do it. I write it right above the things, and then I would say, well, the delta HR equals, 2 moles of CO2 times the 213.8 joules per mole Kelvin, that's the product side, minus the 2 moles of CO, right, times the 197.6 joules per mole Kelvin, right, plus the oxygen term, which is 1 mole of oxygen times the 205.0 joules per mole Kelvin. Okay, if you do all that, I have the numerical answer here, pretty figured out for us. No, I don't. I had it and I erased it. Oh my God, was it? Oh, did I record none of that? Oh my gosh, I thought I was recording. Here we go. So here are the numbers that I looked up for my carbon monoxide, oxygen, carbon dioxide. Again, it's the sum of the entropy of the product minus the sum of the entropy of the reactants all added together. And again, I see entropy went down when I get my final number, which again, I would have estimated that it would have gone down because 3 moles of gas is becoming 2 moles of gas. And that makes sense then that the real entropy change for this reaction was a negative number. That negative number says that entropy went down. And that, my friends, is not really a favorable change. Entropy going down, having less matter spread, is not a favorable thing. All right? So then you may say to yourself, well, Mr. Eston, why would this reaction happen if its entropy, if the entropy change is not a change that is natural to the way of the world? Well, there must be a favorable energy change for this reaction. It's probably going to be exothermic. And that's what we're going to get into this next one. The last thing that we're going to talk about today is how do changes in entropy and enthalpy result in something called thermodynamic favorability. Like, would this happen on its own? Alrighty, so how do entropy and enthalpy work together to determine this thing called thermodynamic favorability, right? Favorability, basically what's that mean? Again, it means that the process will happen on its own without outside intervention. Again, it doesn't mean that it will happen fast. It just means that it will happen. The rusting of iron is spontaneous, quote, spontaneous. It is favorable. Rusting of iron is a favorable process. I'm telling you it is. But rusting of iron happens very slowly. So thermodynamic favorability just says that the process would happen on its own without any outside intervention. Okay, it doesn't mean it's going to happen quickly. And actually, gentlemen, AP topic 9.4 talks about that exactly. Like, what's the difference between favorability and kinetics? And it's what I just told you. 9.4 is a really easy concept. It's that favorability doesn't mean fast. Okay? The speed of a reaction is determined by its activation energy, yeah? And its whole mechanism and all that, and the slow step. Favorability, you could have the slowest reaction in the world, but it's a favorable reaction. Okay, there, that was 9.4. Okay, that's all 9.4 says. So, here's the thing. If you think about delta H, so how are we going to balance these two? Well, if you think about delta H measures energy spread. And what we say is if delta H, right, if delta H is less than 0, in other words, you have an exothermic reaction, well, we've already said that's favorable. That means that the energy of the system got more spread out because that system sent energy out into the surroundings, right? Now, the surroundings end up gaining that energy, right? But you can think of the energy as being spread out from the system to the surroundings, okay? And then, so that's what would be a favorable enthalpy change. We already said that matter likes to be more spread out, and we measure matter spread by the change in entropy, and we want, so a change in entropy that's greater than 0. Okay, now there's no name for this. There's not like a entropothermic or exoentropy, right? There's no term like that, okay? So the bottom line is that if your change in entropy is positive, then that is going to be a favorable process for entropy. Now we got to put the two of them together, okay? So this is a favorable energy spread, and this is a favorable matter spread. And so we got to put the two of them together. So let's think about it. If the value of delta H is negative, that means less than 0, and the value of entropy is positive, well, that's two favorable changes, yes? This is favorable, and this is a favorable change. This reaction, my friends, would be thermodynamically favored because both changes that happen. So what would happen in a process like this would be that energy would go down and the matter would get more spread out. It's the best of both worlds, right? Yeah. Not to quote, Hannah Montana or whatever, right? Isn't that something like that? Hannah Montana, best of both worlds, whatever. Now, what if we had a process that was endothermic, not favorable, and also at the same time, the entropy went down. It became less spread out. Well, this process would not be favored. Would it be favored? Hell no. Okay? This is not going to be a favored change. It doesn't mean it can never happen. It just means you're going to have to intervene. You're going to have to add a bunch of energy to it, maybe, to get it to happen. Okay? Now, if you think about this, then that's where they're opposite signs. Okay? If they're both favorable, though, changes, that's yes. If they're both unfavorable, it's not thermodynamically favored. And when we say favored, we mean thermodynamically favored. Okay? All right. Then what happens, though, if you have a negative delta H and a positive delta S? I'm sorry, wrong. Negative delta S. Negative delta S. Well, or you have this is a favorable change and this is an unfavorable change. Or what if you have a positive delta H, unfavorable, but a positive entropy change? This is unfavorable, and this is favorable. And then the question is, the thing about the thermodynamic favorability is, maybe it might be favored, and it turns out they will be favored under different conditions, different conditions, especially of temperature, okay, will make these either favorable or not. But at this point, it's a maybe. So I always think of when the signs of delta H and delta S are the same, we're going to need some more information. You know what that more information is? Next lecture. Okay? We're going to calculate. It turns out, we're going to take the value of delta H for a reaction, the value for delta S, we're going to combine them into an equation. And that equation is going to tell us once and for all, under a certain condition of temperature, would these ones where the signs of delta H and delta S are the same, would they be favorable or not thermodynamically at that temperature? These are favored at any temperature. When you have negative delta H, positive delta S. Positive delta H, negative delta S, not favored at any temperature. For these, where the signs are the same, where one is favorable and one is not favorable, okay, we're going to have to rely on something called the Gibbs free energy. And my friends, the Gibbs free energy is going to be the change in energy is going to equal, I'm sorry, that's wrong. I'll give you the equation so you can see how it works. The Gibbs free energy, which is going to be called the delta G, hey, for once the symbol matches the name, right, is going to be the delta H for that process minus the temperature times the delta S. So this is where temperature is going to get involved. So we're going to combine, we're going to do a calculation on the enthalpy change for the process and the entropy change for the process, and we're going to get a number. And the number, the numerical value of that thing called delta G, or the Gibbs free energy, will tell us whether the process is spontaneous at that temperature. No, I'm sorry, not spontaneous, is favorable at that temperature. You see, even I grew up learning the word spontaneous. I'm still saying spontaneous, okay? All right, so that's it for entropy.